right, so your little half sheet blue, this is going to go on page 130 in your ISN. This is your reference sheet for classic polar curves, all right? There's definitely other things you could graph, but these are like the classic ones that you would use at the beginning anyway. We've already talked about circles, okay, and we've graphed some of those and got some information about those. Your next category here, do you pronounce that limicons? Is anybody in here in French? What is that fancy C called? This C right here with the little tail on it? Isn't that a French thing? What's it called? You don't know. Ugh. Okay. It's something. But you pronounce it limicon. I don't know. The fancy C does that. Makes that S sound. So notice these graphs here. You see with the tail? That's what it's called. The French are very creative. Okay. So we've got A plus or minus B times the cosine of theta. So if you have a plus or minus situation in there with either sine or cosine, there would have to be a number that is A. B could be 1. But if you have that in there, that throws it into the limicon category. And then you can have different kinds of limicons depending on the ratio of A to B. Notice here that A and B are always positive. So you can have a minus sign in there, but when you talk about these ratios, A and B are positive. So if A over B is less than 1, you get this limicon with the inner loop. And from a very straight-laced and innocent little calculus teacher that's a rock star as a teacher, she calls this the butthole graph. So we think it's hilarious that she calls it that because of all people. But anyway, you got the little loop in there. You can think of it however you want. And then you got the cardioid, which looks like a heart, like cardia, like your heart, right? So it looks like a heart, but it's not pointy at the bottom. Then you have a dimpled limicon that does not hit 0 here. And so it's dimpled in a little bit like a heart. But then you have a convex limicon, which is puffed out, so it's kind of like a wobbly circle. So you have a category of limicons, but then there's different things that could happen as far as your graph is concerned. Then we have the roses, okay, and the roses can have different numbers of petals. So if you see, this is cosine 3 theta, and we have 3 petals, 2 theta, and we have 4, 5 theta, and we have 5, 4 theta, and we have 8. So if it's an odd number, whatever that number is before theta, that's how many petals you have. If it's an even number, you have 2 times that many petals. Okay, it's just the way that that works. Then we have limniscuits. I think about like limp biscuit, limniscute. That's how I remembered how to say it, or I can't remember how to pronounce it. So they kind of look like 2-petal roses, but you notice how they're more ballooned out. Okay, so they're not quite as pointy as the roses are, but they're tilted depending on whether it's cosine or sine. Then we have the spiral of Archimedes, where we have a theta in there, but we don't have sine or cosine that goes with it. So you're not expected to memorize these right now. You're just expected to be able to use this to be able to classify them so that we can more easily graph them and know some other things about them. Eventually, you'll just kind of know what they are once you use them more often, but we're not there yet for sure. Okay, so keep this handy because you're going to need this today, and then it's going to go on page 130 in your ISN. This is going on 131. So we are going to classify and graph the polar curves. We're going to start by classifying them, and we'll do a few together, and then I'll let you do some. So let's look at number 1. It's r squared equals sine 2 theta. So if you look at your little graphic organizer, you only have one set that has the r squareds in it, right? So that means that this has to be a limniscate. Make sense? What do you think about number 2? Is it a circle? It's a rose. It's a rose because these look very similar to circles, except if you have a number in front of theta, that's what makes it a rose. And how many petals would this rose have? 4. Good. This would be a 4-petal rose. So then let's look at number 3. We have the plus or minus, which throws it into the limicon category, right? So then we have to look at the ratio of A to B. So that would give me 4/3, which means it would be in which one would it be? Dimpled, yeah, because 4/3 is between 1 and 2. So this would be a dimpled limicon. Okay, any questions about how we got any of that stuff? All right, so I'm going to give you a couple minutes, and I want you to start to fill in the rest. I may not give you enough time to finish it, but we'll talk about the last ones if you don't have enough time. How did I get 4 petals? Because if it is even, if n is even, then it's 2 times the number. So that's a 2. So since that's an even number, that's why it's 4 petals. That make sense? No, I leave it on the, thank you though. I leave it like that sometimes too, so the people watching the video have to actually think. And I just copied on what I do. So if you are watching the video, you should be filling these in too. Okay, I don't want to have to rush through the graphing because I felt like I kind of had to rush through the end last period. So I know I probably didn't give you enough time to finish, but hopefully you got to think through a couple of them and we'll think through all of them together. So tell me about number 4. What do you think about number 4? What is it? It's a circle. Good. All right, what about number 5? Spiral. So it's the spiral of Archimedes. We'll talk about Archimedes a little bit too. All right, so we got the 3 plus 3 cosine theta, which means throws it into the limacon category. What kind is it? Cardioid. Okay, so the cardioid is the only one that doesn't have limacon in the name. So we usually write it on in parentheses there. Okay, so that makes sure that we know the category it's in. What about number 7? It's a rose. How many petals? 7. Good. So this is a 7-petal rose. That's an odd number, so that is the number of petals. So 8, I've got those 2 terms. That means it's a limacon. What kind? It's got, my ratio would be 1/2 with the inner loop. Good. So this is a limacon with an inner loop. Everybody understand how we got that? Yes? Okay. All right, so then number 9. What do we think that is? Circle. Good. And then 10. Good. That would be a convex limacon. Because we, the ratio is 2. So. Any questions about any of those? We're all good? Awesome. Let's look how this is going to help us with the graphing. So if you remember when we graph, we can look at symmetry, we can look at maximum R values, all those sorts of things. Of the stuff that we have done algebraically working up to this, we've had to find the R values and the zeros. Those weren't so bad. The symmetry was kind of a pain in the butt, right? So here's the good news. If we can find the maximum R values and the zeros, and we know what kind of curve it is, that right there will tell us what kind of symmetry it has, and we don't have to test it every single time. Does that make sense to you? I'm not saying you'll never have to test symmetry again ever, but we have other ways to know what the symmetry even is if we know what our curves are. So let's look at number 11. We've got, so this has to fall into the limacon category, right? Which kind? Cardioid. Very good. So this is a cardioid. Yes. That's okay. I know, it's all good though, but you get it now. It's all right. Ding. That's okay. It's good when the light bulbs go off. As long as the light bulb finally goes off, it's all good. All right. There's a lot of things related like that. I think that sometimes y'all don't get those connections. But all right, so the first thing I'm going to do is not symmetry, because that was a lot of work that maybe I can avoid. But I can't guess at my maximum R values, right? So I need to figure those out. Remember, to do that, we said that -1 is less than or equal to the sine of theta, which is less than or equal to 1. And then we say if sine theta is equal to -1, then the absolute value of r is equal to the absolute value of 2 minus 2 times a negative 1. So negative 2 times negative 1 is a positive 2. So this gives me the absolute value of 4, which is 4. By itself, that didn't tell me much because I got to know if it's the biggest, so I have to do the other. So I have something to compare. Then I say if sine theta is equal to a positive 1, then the absolute value of r equals the absolute value of 2 minus 2 times 1, which is 0. So now we can tell which one's the biggest, right? That would be 4. So then we have to figure out what the angle is at that maximum r value. So 4 equals 2 minus 2 sine theta. So this gives me 2 equals negative 2 sine theta. So negative 1 equals sine theta. So what would theta equal? 3 pi halves. Good. And that's it. So we can say for our maximum r values, the absolute value of r is equal to 4 at theta equals 3 pi halves. Everybody with me? Okay, so now we're going to find our zeros. So I say 0 is equal to 2 minus 2 sine theta. And that's negative 2 equals negative 2 sine theta. So 1 equals sine theta. What's theta equal? Pi halves. My zeros, theta equals pi halves. All right, so let's plot a couple of things here. I've got my maximum r value, right? And it's at it's 4 at 3 pi halves, but you have to pay attention to, because remember, that's the absolute value equals 4. Make sure you're paying attention to what the radius actually was. It was a positive 4, because if it's a negative 4, it changes it, all right? So I have a positive 4 at 3 pi halves, so I can plot that point. And then if you have a 0 at all, you can plot the 0, because when you plot a 0, it doesn't really matter plotting-wise what angle it comes from, because it's all going to be in the same spot. So given the fact that we have a cardioid, and we have these 2 points plotted, can you tell me what kind of symmetry it has? It's the pi halves, right? So it's the theta equals pi halves. We could confirm that algebraically, but we totally don't need to. Right. So I need to plot some more points, though. On the activity that you did yesterday, just you getting the general shape and the general idea, I was fine with that. Those graphs don't have to be perfect and beautiful. These also don't necessarily have to be perfect. Also, before I forget, because I already forgot beforehand, for y'all, the last question in Desmos had a question, but it didn't have anywhere for you to put the answer. Some of y'all probably already figured that out. I have since fixed that. I didn't realize I do that, but once I fix it, because you already have the code, you don't see the changes I make after I give you a code. So you can't put an answer in there, but I really wanted that answer. So and there's no room on that green paper. If you'll just write it out on a separate sheet of paper, a couple sentences, and put your name on it, you don't even have to staple it, just turn it in with your green paper. It's easy questions. I mean, they're not like you have to do math. It's just more some feedback about what you did. So if you'll just write it on a separate sheet of paper, sorry, I forgot the blank, and I can't change it at this point. Anyway, but on here we want these a little bit better. So this is going to be kind of like halfway between graphing and sketching, just a little bit more accurate sketch, but still not a perfect, beautiful graph that we could like build bridges and stuff off of and be super accurate, but we'll be fine. As we go around here, I want some other points. 0 is a really easy one to start with. So we'll start by using 0 as my angle. If I substitute 0 in here, the sign of 0 is 0. So that means I get 2 minus 0, which is just 2. So at 0, I have a radius of 2. This symmetry right here allows me to plot another point because I have to be 2 away on the other side as well, right? So then I'm going to go around and we can just use what I would consider like the easy values. Like the prettiest value for sine would be the pi 6, right? What's the sine of pi 6? 1/2. We don't have to worry about the square roots and stuff. So the sine of pi 6 is 1/2. 1/2 times a negative 2 is negative 1. So 2 minus 1 is 1. So at pi 6, I'm at 1. Because of the symmetry, at 5 pi 6, I'm also at 1. given the fact that I know that it's a cardioid and that's like that top part of the little heart looking thing, I think that's enough points on the top part. I think I'm good. I can get a sketch in there. But when I come around here, I can use 7 pi 6. What's the sign of 7 pi 6? Negative 1/2. So negative 1/2 times a negative 2 is a positive 1. 2 plus 1 is 3. So at 7 pi 6, I have a radius of 3. Which means over here at 11 pi 6, my radius is also 3. Now, this really looks like a heart right here, but a heart like you would draw if you were just going to draw a heart. Remember that these do not come to a point. Okay, so it kind of looks like a heart, but not exactly. So it would help us to graph some other points on here, but you don't have to. You just have to make sure that you are making an honest effort to make it look pretty circular down at the bottom like that. And then when you come up here, these points here kind of help lead you into exactly where it needs to be, like so. And again, not an art class, make an honest effort, and you'll be fine. Any questions at all? Okay, so I say that all the time. Any questions at all? And y'all rarely ask me a question. And then people come into tutorials and other things are like, I never did understand this, and I don't get this. Well, ask a freaking question, okay? Ask me while I'm going over it if I need to say something again or whatever. Just ask. It's okay. You're most likely not the only one out thinking that, whatever it is that you have a question on. Are we good? All right, speak now or forever hold your peace. All right, let's look at the next one. All right, so what is this? A circle, okay? This is a circle, and we're going to start by using our maximum R values. Negative 1 is less than or equal to cosine theta, which is less than or equal to 1, okay? So we know that if cosine theta is equal to 1, negative 1, we'll start with negative 1, like we always do. Then the absolute value of R is equal to the absolute value of 3 times a negative 1, which is the absolute value of a negative 3, which is 3. And just FYI, last period I skipped this because I'm like, we know it's negative 3. I just went straight from here to 3. And then I realized on the next step that was kind of a bad idea. So I'll show you why when we get there. But that's why I wrote that down, even though I already kind of knew what it was. So then I'm going to say if cosine theta is equal to a positive 1, then the absolute value of R is equal to the absolute value of 3 times 1, which is the absolute value of 3, which is 3. So I get the same number. When that happens, I have to do this twice then, right? So I have to start by using the negative 3. So negative 3 is equal to 3 cosine theta, which means I get negative 1 equals cosine theta. And what does theta equal? Pi, okay? So that's part of it. Then I use the positive 3. 3 equals 3 cosine theta. So 1 equals cosine theta, which means that theta equals what? 0 and 2 pi. So then over here I can say the absolute value of R equals 3 at theta equals 0, pi, and 2 pi. Then I need to find my zeros. So 0 is equal to 3 cosine theta. So 0 equals cosine theta. Theta equals what? Pi halves and 3 pi halves. Okay, everybody good with all that so far? So when you come over here to graph, that's when this not necessarily being written there can throw you off a little bit, because you have to pay attention to this radius here, because yes, the maximum R value is 3, but it came from a negative 3 and a 3 because you're taking the absolute value. So you have to make sure that you're not using a positive one, you should be using a negative one, and so forth. Because this pi goes with the negative 3, and these go with the positive 3. So at 0, I have a radius of 3. At pi, I have a radius of negative 3. I already have that point, right? And then at 2 pi, so it just keeps repeating. So remember, some of this will repeat because we at times are going to be finding more than we need. We just don't know what we need yet. We don't know how to figure that out. And also, sometimes when you actually apply this stuff, and we will look at why you care and how we would apply this, but when you apply this stuff, sometimes you might want it to repeat, to go through more than one cycle, so it just kind of depends on what's going. But for graphing, you wouldn't necessarily have to make it repeat. Okay, so I've got that point, and then I've got a 0 somewhere. Here's my 0, right? Knowing that it is a circle and these 2 points exist, what type of symmetry am I going to have here? Polar axis. Now remember, there's a difference between pole and polar axis. The pole is like the origin. It's just the point. So that would be your rotational symmetry of 180. But then this is the polar axis. So it has polar axis symmetry. So when I want to go around and try and just maybe use the decent numbers, I'm using cosine. So with cosine, the angle that gives me a decent value is the pi thirds, right? Cosine of pi thirds is 1/2. 3 times 1/2 is 1.5. So at pi thirds, I'm going to be at 1.5. I have symmetry, so that means at 5 pi thirds, I also have that. Now, we know it's supposed to look like a circle. Honestly, plotting more points isn't going to help because it's going to look all wonky no matter what you do. It actually might be better if you didn't have as many points. You know what it's supposed to look like. You have these points that are easy to graph, and then we can just go in here and graph the circle. And my circle looks better using less points. Because when you do the other ones, you're estimating anyway. So when your estimation's off a little bit, it just makes everything look funky. So we just do the best we can to get the circle. Okay? Any questions? Anything? Now that one, if you knew more, if you understood more stuff about it, knowing that it's a circle and which way it's supposed to lay, you may not even have to do all the work that we did. The rest of them you're definitely going to have to because you're just not going to know enough about them. All right, let's look at the next one. What is this thing? It is a rose. How many petals? 3. Okay, so we have a 3-petal rose. All right, so -1 is less than or equal to the sine of 3 theta, which is less than or equal to 1. So say if sine of 3 theta is equal to -1, then the absolute value of r is equal to the absolute value of 5 times the -1, which is the absolute value of -5, which is 5. Then if sine 3 theta is equal to 1, absolute value of r is equal to 5 times 1, which is the absolute value of 5, which is 5. Okay. So I got to do it twice. So I'm going to start with the -5 here. So -5 is equal to 5 times the sine of 3 theta. This is going to give me -1 equals the sine of 3 theta. I do not divide both sides by 3 at this point. I take the sine inverse, which is going to give me 3 theta equals what? 3 pi halves. Right. Do I have to have more than that? How many times do I have to go around the circle? 3 times, okay? So that one time here, oops. Dang it. Okay, that one time here I am at 3 pi halves, right? So then when I go around again, what's that going to be? 7 pi halves. Because this would be 3, 4, 5 pi halves, 6, 7 pi halves, right? So 7 pi halves, and then 11 pi halves. All right, so it was asked of me again yesterday, last period, why do we put so many? Why are we going around the circle? So I want to remind you that if theta itself has to be between 0, oh my gosh, and 2 pi, right? Then 3 theta, like if I multiply that by 3, this is still going to be 0, but this is going to be 6 pi. Okay, so 3 theta has to go from 0 to 6 pi because I'm about to divide everything through by 3, And when I do that, theta has to be between 0 and 2 pi. Does that make sense? So this number just tells you how many times to go around the circle. You can think about it that way. All right, so we get that theta is equal to, well, 3 pi halves divided by 3 is what? Pi halves. And then 7 pi 6, and then 11 pi 6. Okay, so there are my thetas for that negative 5. Then I have positive 5. That's equal to 5 times sine 3 theta. So 1 equals sine 3 theta. 3 theta equals, what's the first one it's going to give me? When is sine 1? Pi halves. So I got pi halves, and then what? 5 pi halves, and then 9 pi halves. Then I got to divide everything through by 3, and I get that theta is equal to pi 6, 5 pi 6, and then what's 9 pi 6? 3 pi halves. So I can say the absolute value of r equals 5 at theta equals, I'm going to put these in order, pi 6, pi halves, 5 pi 6, 7 pi 6, 3 pi halves, and 11 pi 6. Everybody with me so far? All right, I'm going to put my zeros up here so that I don't stand in front of the board. So I'm going to do 0 equals 5 times the sine of 3 theta. And so that means that 0 equals the sine of 3 theta. So theta equals, or 3 theta equals rather. When is sine 0? 0, and then pi, 2 pi, 3 pi, 4 pi, 5 pi, and 6 pi. So because these are already in order, we're going to just, instead of writing our answers here and rewriting them, we'll just write them in the zeros over here. So theta is equal to, when we're divide by 3, it's going to give me 0, pi thirds, 2 pi thirds, pi, 4 pi thirds, 5 pi thirds, and 2 pi. Everybody good so far? Any questions at all? Okay, so let's plot some points. So I'm going to start with, when I do these, you got to make sure that you're paying attention to the fact that these go with the negative 5, these go with the positive 5, right? So when I start at pi 6 has a radius of a positive 5. Bam. My next one is pi halves. Pi halves goes with the negative 5. So at pi halves, I have a radius of negative 5, and I'm down here. Then I go to 5 pi 6. 5 pi 6 has a positive 5 radius. Then at 7 pi 6, I have a negative 5, and I'm starting to repeat. What if you know what it looks like, and you're starting to repeat, then you could probably stop. This is supposed to be a 3-petal rose. Am I going to have any more maximum R's on there? No, that's it. The rest, they're just going to repeat right on top of each other and kind of alternate back and forth between positive and negative. So I'm good, and I can stop worrying about plotting points. I have zeros. I have a lot of them, but they're all just going to plot right on top of each other right there. Okay. So knowing that it's a rose, and knowing that we have these points on there, what kind of symmetry do you have? Theta equals pi halves. It is not pole symmetry. It does have rotational symmetry, but remember, pole symmetry is that 180. If you turn your paper upside down, is it going to look the same? Nope. And if you're not sure, turn your paper upside down and see if it looks the same. So it's not. So rotational symmetry exists, but not in the way we need it to. So it does have line symmetry right down here at theta equals pi halves. So that symmetry could be helpful here. Now, as far as plotting extra points, The nice values we like for sine go with pi 6, and we've sort of already used that one, and so we're not going to actually be able to do that. But on the roses, we're going to graph them kind of like you graphed them before you even knew what you were graphing, knowing that from here at pi 6, my first 0 is at pi thirds. So I have to have this skinny petal that cannot cross pi thirds. I have to rotate around and hit 0 before I come to pi thirds. The 0 on the other side of pi 6 is 0. So I have to rotate around and come up and hit 0 before I cross the angle that is 0. When I get to 5 pi 6, right, I got a 0 at 2 pi thirds and at pi, so it's got to be skinny like this again. And then you just repeat yourself going around like this. And they're not really that pointy. I don't know, mine always look too pointy. If you look on this, they're more curvy. They're not really ballooned out, but everything's a curve. Nothing comes to a point on this stuff, even if mine look like it. Questions? Okay, so the roses are the ones that you kind of get to not have to plot any other points on there. All right, let's look at 14. Any questions first? All right, so on 14, what is this? Okay, it's a limison with what? The loop. Okay, so it's a limison with an inner loop. Okay, so I have to start off with -1 is less than or equal to sine theta, and it's just theta. There's not a number there. We really like it when it's like that. So that I can say if sine theta is equal to -1, then the absolute value of r is equal to the absolute value of 2 plus 4 times a -1. So 4 times a -1 is a -4 plus 2 is a -2. So I get 2. So then I do if sine theta is equal to 1, then the absolute value of r is equal to the absolute value of 2 plus 4 times 1, which is equal to the absolute value of 6, which is 6. So 6 wins, right? And I'm going to have to find my r. So 6 equals 2 plus 4 sine theta. I'm just going to solve that. So I get 4 equals 4 sine theta. 1 equals sine theta. So if the sine of theta equals 1, what's theta? Pi halves. Okay, and there's just one of them. So I have an absolute value of r is equal to 6 at theta equals pi halves. Okay. All right, so now I got to find my zeros. So for my zeros, I get 0 is equal to 2 plus 4 sine theta. So I get -1/2 equals the sine of theta. So that means theta equals what? 7 pi 6, yeah, 7 pi 6 and 11 pi 6. Everybody good so far? All right, so now let's plot some stuff. I'm going to plot my maximum r value. I know the absolute value of r is at 6. Make sure you pay attention to whether or not that 6 is positive or negative for the radius itself. And so at pi halves, I have a radius of a positive 6. It's up here. I have a 0 somewhere, so I have a 0. Knowing that this is a limison with an inner loop, bless you, my symmetry, what kind of symmetry we got? Yeah, pi halves. Theta equals pi halves. All right, so we are doing sine, so we'll use the pi 6 again, right? So the sine of pi 6 is 1/2 times 4 is 2 plus 2 is 4. So I have a radius of 4 at pi 6, which means I also do at 5 pi 6. Okay, everybody okay with that? I also like 0. I usually start with 0. I don't know why I didn't, but so 0, the sine of 0 is 0 plus 2 is 2. So I have a radius of 2 at 0, which means I also do at pi. So knowing that it's a limit sum with an inner loop, I know it's going to kind of bubble out here, and it's going to have to drop down here a little bit. I could try and use my 7 pi 6 like I did on the other one, but guess what? 7 pi 6 is a 0. So what I know is that it drops down, but it can't go any farther than that. It's got to, have a smaller one and come in there and hit it there. And it has an inner loop. Guess what? This right here gives you your inner loop. So if I do -2, like we found this to get our maximum R, right? But if I take -2 and I figure out where the angle is, -2 equals 2 plus 4 sine theta. This is going to give me a -4 equals 4 sine theta. And so I get -1 equals sine theta. So what does theta equal? 3 pi halves, right? So that means I have this point at -2, 3 pi halves. So 3 pi halves, and I go -2, that means I'm right there. So we know what our loop looks like. Okay? So remember, it's not pointy. It balloons out to almost looking like a circle up here. And then it's going to come down kind of like a cardioid and come in up there, but it's going to loop around and then come back out like that. And how circular your loop is, you don't necessarily know that. We don't have to, go and do extra points or anything like that. Okay. Any questions at all? Good? All right. You sure you don't have any questions? All right, so here's the deal. You have, there is another set of notes, but the good news is they're already filled out. Because I wanted you to see these other graphs, but I didn't want to spend days graphing these with you. So I'm going to give you the second part of the notes. You can put this goes on the next page, which I think is 132. And it's all worked out and everything. They're not just graphed. I mean, you already have the graphs on the blue thing. But that way, if you needed to see extra examples, they're there. But we don't have to go and do all of them. George is lost. Okay, let me pass these out, and then I will come help him. Then George should have asked a question. I'm going to start punishing y'all when you don't ask me questions.